Kia ora team. So today we're going to do a quick session talking about logarithms, okay? So what are logarithms? The easiest way to think about logarithms is in terms of exponential equations, all right? So first of all, what's an exponential? An exponential equation is a number, or a equation I should say, with a number on the bottom, in this case let's call it 2, a power on the top, in this case let's call it 3, and of course what this equals. So 2 to the power of 3 equals 8. Now we can call that an exponent, all right? And why is it an exponent? Because it's the same number, 2, being multiplied by itself 3 times, okay? So in this example, we have this number here, the 2, being referred to as the base. This guy up here, the 3, is being called the power or the exponent. And then this dude here, number 8, is being called the result, or what it equals, right? So we'll call that the result. Now, we know that with these sorts of equations, we can see a pattern of these arising eventually. So 2 to the power of 3 is 8. Let's examine 2 to the power of 4. 2 to the power of 4 is just 2 times 2 times 2 times 2. Okay, good. That gives us 16. What about 2 to the power of 5? Well, that's 32. 2 to the power of 6, 64. So now you're seeing the pattern. Each of these is doubling every time we add plus 1 to the exponent, okay? So that shouldn't be too surprising. But what does that actually mean? If they're doubling as we go down, what's going to happen if I start moving up the chain? So 2 to the power of 2, we know to be 4. 2 to the 1 is, of course, 2. And 2 to the negative 1, or sorry, 2 to the 0, I should say, is, of course, 1. Just as any number to the power of 0 is 1 itself, okay? So what I like to think is happening here is these exponent terms, it's kind of like time or for how long have we been doubling in this case. So at time equals 0, or at 0 iterations, 2 to the power of 0 is equal to 1. So we just have 100% of what we started with. It's just 100% is what it always was. Pretty basic. Once we do 1 increment, it doubles. Once we do 2 increments, times 4, 3 increments, times 8, so on and so forth, okay? Now, why do we care about all this? Well, this underpins the whole framework of logarithms. So, a logarithm is effectively a different way to write an exponential equation. So rather than write the whole word logarithm, which takes a while, I'm going to write this equation here. Actually, I'll write this one. 2 to the 3 equals 8. I'm going to write that as log 2 brackets 8 equals 3. What does that mean? Well, that means that the number base 2 is my base here. And you'll notice that that's written below the log number here, not next to it. 2 is my base. 8 is my result. And what does this equal? It equals the power, okay? So what this is actually saying is if I have a number, if I have an exponent equation to base 2, and it ends up at the number 8, how many increments have we gone through? What was the power of that equation? So log 2 base 8 equals 3 means if I have 2 and I raise that to the power of something and it equals 8, what was that something? Right? So 2 to the power of 3 gives us 8. Likewise, let's look at this one. 2 to the 5 equals 32. I could write this as log base 2 again. And in brackets, I'm going to write the result here, 32. And of course, this is going to equal the power, which we know to be 5 here, all right? Good. Okay. Cool. So why do we care about all this? If a number, let's call it, let's say we have 3 to the 4. What does that equal? 3 times 3 is 9. 3 times 3 is 9. So this would equal 81. How could we rewrite this in terms of logs? Well, first of all, we ask ourselves, what's our base? Our base is 3. So we have log 3. In brackets, we're going to put 81. And of course, that is going to equal 4. Okay, cool. What if I gave you something as a log equation and asked you to translate it backwards? If I said log 4, 64 equals 3. What would that mean? Well, you'd be able to interpret that as what's the base? Well, the base is, of course, 4 here. The power is written here as a 3. And that would equal 64. 4 times 4, 16 times 4, 64. So yes, that's mathematically correct. Haven't made any mistakes. Good here and good here. Okay. What if I asked you to find the power of, let's see. What if I said, log 4, 4. What would that equal? What we're saying is we are increasing by a factor of 4 every time we do an iteration, but we also end up with 4, okay? So translating this back into our everyday exponential equation, what this is telling me is 4 to the power of something, whatever this might be, equals 4. What's the only way that equation can be completed? Well, of course, that has to be 1, doesn't it? So 4 log 4 equals 1. So that makes sense. So not only is that true, but we can now talk about a few different log rules that take place, okay? So this one, log 4, 4 equals 1, is just a classic example of this rule here, okay? If we have any number log to some base, and then in brackets we have that same number that is the base, that has to equal 1, all right? For the same reason, we start with a number, we iterate it one time, it has to end up with the same number, okay? Log 4, bracket 4 has to equal 1. So we've done that, we understand that one, that's good. Now what about this rule? Log to the base k to the number 1 equals 0. Why does that make sense? Well, let's think about it. If I take log, if I take a k as my base, 0 is my power, does that equal 1? Yes, because any number to the power of 0 equals 1. So that's mathematically consistent. Good. What's an example of that? Well, log 3, bracket 1, has to equal 0. Let's see. 3 to the 0 equals 1. Tick. Correct. Okay. A couple of other rules we'll go through here is log k, and in brackets we have 1 over k to the power of x. Now that has to equal negative x. Now why is that correct? Well, let's think about it. I could take this log k, bring this up here, log k to the bracket 1 over kx what does that actually equal? This actually equals log k, bracket k to the negative x, doesn't it? Right? Now, if I'm asking myself, with a base of log k, if I start with base of log k and I end up at k to the negative x, what's the power? Well, it's being told to me, isn't it? It's got to be k to the negative x. Sorry, it's got to be negative x is the power. So that's consistent here. What could that look like in practice? Well, if I have log to base 5 and my final result is 1 over 5 squared, we can rewrite that as 5 to the negative 2. So what's the power going to be? Well, we already know it's negative 2 here because we've seen it here. So that makes sense. Okay. Now, this last example we have, this last log rule we'll go through is log k n k m. Okay. Now we know that when we have this type of surd form, or nth root, k to the power of m, we can always rewrite that as k to the m over n. So now we've identified the power of this. So that has to be m over n, doesn't it? What does that look like in practice? Well, suppose I have my example here. Look at this guy. Log 4, bracket third root of 4 squared, can be written as log 4 to the power of 2 over 3. So what's the power in that instance? Well, of course, it is 2 over 3. All right. So that's a bit of a rundown of the basic rules of logarithms.